Welcome back, everyone, to the online Gas and Matroids seminar. Today, we're happy to have Kevin Grace from Vanderbilt University. So take it away, Kevin.
Okay, thanks a lot, Zach, and to James for the invitation to speak. And so this is some joint work with Nick Bertel. And so I will be talking about some generalizations of the class of spikes. And so since we're talking about generalizations of spikes, let's go ahead and make sure we all know and are familiar with spikes themselves. What I'm calling a spike is more specifically a tipless spike. There is which is a matroid with a ground set that can be partitioned into pairs, such that the union of any two pairs is both a circuit and a co-circuit. Okay, so we have a union of two pairs. So these are circuits with 4 elements and co-circuits with 4 elements. So if I take these pairs here, so the ground set is partitioned into these pairs. If I take 2 of those pairs, that is a co-circuit. It's also a circuit. But if I take any pair of elements at all, well, either that pair of elements is one of these pairs up here, in which case, if I take any other pair, the union is both a circuit and a co-circuit of 4 elements. Or if I just take any 2 generic elements, well, each of those is contained in one of these pairs that are part of the partition. And so you take each of those 2 pairs. The union is both a circuit of 4 elements and a co-circuit of 4 elements. Okay, so any pair of elements is contained in some 4-element circuit and some 4-element co-circuit. And with the way that these spikes work, the number of these pairs is the rank of the matroid, so the rank of that spike. Okay, so here's sort of a generic picture of a spike that's supposed to have rank at least 5. So I've got at least 5 pairs here, and these dots here indicate that there could be other pairs. By the way, do you see my mouse moving around? Okay, good, great. Okay, so just sort of a generic geometric picture here of a spike with at least rank 5, at least 5 pairs. Okay, so some more information about spikes. They appear often in the matroid literature. And they kind of turn out to be an unexpectedly wild class of matroids. So they can be a little bit difficult to get a handle on. But they're important in problems involving connectivity. So for example, this results by a nice group of LSU folks, Ding, Oporowski, Oxley, and Vertigan. For any integer n at least 3, there's going to be an integer k dependent on n. Such that every 3 connected matroids, so this is a result about 3D connectivity, with at least k of n elements, is going to have a minor isomorphic to one of these matroids here, or to a spike of rank n. Okay, so we have these several exceptions, but then other than that, it's going to be isomorphic to a spike of rank n. All right, so spikes show up in problems involving connectivity. But let's think a little bit more about connectivity in general. So again, specifically 3 connectivity here. This is the famous wheels and whirls theorem of Tutt, which is that the only 3 connected matroids with no element whose deletion or contraction preserves 3 connectivity are wheels and whirls. And in wheels and whirls, every element of the wheel is contained in both a 3-element circuit and a 3-element co-circuit. So I'm guessing maybe most of us are familiar with wheels and whirls, but just in case, here is the graph W8. This is the wheel W8. And so the matroid you get from this would be the graphic matroid of this graph. And so every these spoke edges here are contained in both a couple of 3-element circuits. So these 3-sided triangles here, 3-element circuits. So 2 of them. But they're also contained in a 3-element co-circuit, this triad. So if I delete these 3 edges here, then the rank of my matroid goes down by 1. So it's contained in a 3-element circuit and a 3-element co-circuit. Similarly, the rim edges here, they're contained in this 3-element circuit right here. But then this rim is also contained in a couple of 3-element co-circuits. So this triad of edges incident with this vertex here, and this triad of edges incident with this vertex here. Okay, so that's a wheel. So that's just a graphic matroid. But a whirl is obtained from a wheel by relaxing the circuit hyperplane consisting of these rim edges here. So in other words, so these rim edges form a circuit. So it's a single cycle, but also a hyperplane because there's a maximal set of rank less than the rank of the matroid. So what we do is we construct a different matroid that is no longer graphic, but the set of rim edges is going to become a basis rather than a circuit of the matroid, because the number of edges here is going to be the number of the rank, and so we're able to do that. And all the other smaller circuits and co-circuits are still there, so we still have every element is in a 3-element circuit, a 3-element co-circuit. So that's what we have here. And then another result of a student of Jeff Whittle's, Alan Williams, is that the only 3 connected matroids on at least 13 elements with no triangles, no triads, and no pair of elements whose deletion or contraction preserves free connectivity are spikes. Okay, so here again is where the spikes are coming in with connectivity. But wheels and whirls and spikes are examples of matroids that have a specific kind of property, which Nick and I for this paper have called the SUTV property. So a matroid that has the SUTV property is one in which every S element subset of the ground set is contained in a U element circuit. So first letters here go for circuits, and every T element subset is contained in a V element co-circuit. So that's this SUTV property. So again, the wheels and whirls theorem has to do with 3 connectivity here. So this is motivated by problems in connectivity, and wheels and whirls have the 1-3-1-3 property. Every single element is a 3-element circuit. Every single element is a 3-element co-circuit. And spikes have the 2-4-2-4 property. Every pair of elements is in a 4-element circuit and in a 4-element co-circuit. Okay, so what else can we study here? So this talk is going to be generalizing this 2-4-2-4 property to S2ST2T. So the U is just double S and the V is double T. So if you have a positive integer S and every set of S elements is contained in a 2S element circuit, every set of T elements is contained in a 2T element co-circuit. Yeah, but there's been some previous work on matroids that have this SUTV property for different values of SU, T, and V. So another student of Jeff's, Joel Miller, he studied spikes. Specifically, more generally, he studied matroids that have this 2-4-2-4 property. And he was able to show that matroids with this property that are large enough are spikes. Right. And so I'm going to tell you more about this S2ST2T property that generalizes spikes. But in between, there was a generalization between those that Nick Bertel, Rucker Campbell, Deborah Chun, Jeff Whittle, and I worked on. And this is where we just generalize this 2 to any integer. And we were able to show that matroids that have this 2T2T property that are large enough have a certain structure. But more recently, Nick and I generalized this a little bit further and dropped this requirement that the S and the T are equal. And by the way, when I say generalize this, I will show you the results in a few slides. But just the point here is that these first 2 papers here are specializations of this more recent result here. Okay, so we don't just have to double the S and the T. Oxley, File, Semple, and Whittle studied matroids that have the 2-4-1-V property. They show that sufficiently large V-connected matroids with this property is going to be the cycle matroid of this complete bipartite graph, KVN, for some integer n. Okay, and there's also a cyclic version of the of this property where we take the elements of the matroid. Well, I say I haven't done this, but you take the elements of the matroid and you put a cyclic order on these elements, and it's only the consecutive sets that need to be contained in a circuit or co-circuit. So the consecutive sets of size S need to be contained in a U element circuit, and the consecutive sets of size T have to be in a V element co-circuit. And more from Nick with Deborah Chun, Tara Fife, and Charles Semple. They studied matroids that have the cyclic S+1, SS+1 property. And then Nick with Charles and Jerry Tuft dropped the requirement that S has to be equal to T in a recent paper there as well. So Nick's done quite a bit of this stuff. And we're going to continue talking about this result here and as well as this too. All right, so the results that we have is that matroids that have this S2ST2T property of sufficient size are a specific type of matroid that we have called ST spikes. Okay, so an ST spike is a matroid that has ground set that we can partition into pairs. And the union of any S pairs is a circuit, and the union of any T pairs is a co-circuit. So this generalizes spikes where any two pairs is a circuit and a co-circuit. Here I can change both of those numbers to whatever I like, S or T. And if there are M of these pairs, then we say this is an ST spike of order M. Okay, so for example, here is a 2-1 spike. So just a very simple picture here. So every two, so I got these three pairs, which I have denoted Xi, Yi. So X1, Y1 is a pair, X2, Y2 is a pair, and X3, Y3 is a pair. And the union of every two of those pairs is going to be a circuit. So the union of those two, any two pairs gives us a plane, and any single pair is a co-circuit. So these are three series pairs here. So these are ST spikes. They generalize they're a generalization of a generalization. So the generalization in between the S and the T are equal. And this was that earlier paper that I mentioned with Nick, myself, Deborah, Rucker Campbell, and Jeff Whittle. And that paper came out of a workshop over in the land down under in Australia. So this has been a few years ago now, but this was a workshop celebrating 100th anniversary of the birth of Bill Tutt. And so there were several of us who got together near Melbourne, Australia, to work on some problems in areas that were of interest to Tutt. And one of those was structural matroid theory. And so this came, a lot of these results came out of this Tutt Centenary Retreat back in 2017. Particularly T spikes, where the S and the T are equal to each other. So using the terminology that I just showed before with ST spikes, a T spike is just a T spike where S and T are equal. So with these folks here, we defined the T spike back then. So here is a 2 spike, or just a 2 spike, or just this is actually just a regular spike, traditional 2 spike. So I've got 4 pairs here. Every 2 pairs is a 4-element circuit and a 4-element co-circuit. Right. So if we look at this picture, what we've got are these things that sort of look like spines pricking into the middle of this picture here. And when we were working on these, we often would draw pictures where we have these little, they look like spines with these 2 dots all together, all over the picture. And we were in Australia, so we got some inspiration from the wildlife there in Australia, and we named these things echidnas. So here's an echidna from some Australian wildlife there. So I got these spines sticking out, So these little spines remind us of these pairs of elements. And so back in this earlier paper, we defined a T echidna. Order n is a partition of a subset of the ground, partition of a subset of the ground set. Okay, so it does not necessarily have to be the entire ground set of the matroid, but it's a partition of a subset into pairs. Okay, so each part of the partition is a pair, so each part has size 2. And the union of any T of these pairs is a circuit. Okay, we called each of these a spine, just to keep up with the echidna terminology. And as good matroid theorists, we stuck the word co in front of that. So a T co-echidna of your matroid is a T echidna of the dual matroid. So this is, so only matroid theorists most likely would pronounce that word as co-echidna. That's how we pronounce it. So another way that we can talk about these ST spikes is that a matroid is an ST spike if there's a partition of the entire ground set. So the entire ground set that is both an S echidna and a T co-echidna. Okay, so every set of S pairs, the union of that is a circuit, and the union of any T pairs is a co-circuit. So here's our results. The result is that there's just some function from natural numbers crossed to natural numbers to the natural numbers, such that if a matroid with this S2ST 2T property has a larger ground set than that function, then M is an ST spike. Okay, and the case where S equals T was proved in that earlier paper. In particular, the case when S equals T equals 2 was proved by Joel Miller, that student of Jeff Little's, which is right there. Okay, yeah, so as I just said, Miller showed that f of 2 equals 13 is best possible. Back in 2014. So a little bit of a sketch of the proof, just to give a little bit of a flavor of how this went. So if M has an S echidna of a certain order or larger, then we were able to show that S echidna actually also has to be a T co-echidna. And I'm actually going to go through the proof of that on the next slide, just to give you a bit of a flavor of how a lot of these arguments go. Okay, so if I have a big enough S echidna, then the S echidna actually also has to be a T co-echidna. We also showed that if M has an S echidna of sufficiently large order, then actually the entire ground set has to be an S echidna and a T co-echidna. So if we have sufficiently large order, we're going to get both the entire ground set will be an echidna and a co-echidna. So if we can show that we have this echidna of large enough order, then we know we have the entire ground set as an echidna and a co-echidna. And we were able to do that using some hypergraph Ramsey theory, K-uniform hypergraphs. So basically Ramsey theory says if I have something really, really large, there's going to be the thing that I want contained in it of sufficiently large size. And so with a hypergraph, so with graphs, you have vertices and edges. With a hypergraph, you have vertices and hyperedges. So the vertices are these pairs of elements in our pairs of elements in our matroid, and the hyperedges are the circuits of the matroid, and we will show that we have enough circuits to make this into a large enough S echidna. Okay, so I told you I would show you the proof of this right here, just to give a flavor of how a lot of these arguments work. And so this technique was used also in that earlier paper as well. Okay, so let M be a matroid with this S2ST2T property. And if M has an S echidna of sufficiently large size, we're going to show that it also has to be a T co-echidna. All right, so this S echidna has N pairs. So I'm going to let J be a subset of the integers 1 through N. That's what this stands for here, 1, 2, 3, all the way up to N. And for each of these pairs, I'm going to denote the elements of that pair as xi and yi. So S sub I consists of both xi and yi. Okay, so in order to show that I have a co-echidna of order of a T co-echidna, I need to show that every set of T pairs, the union of that is a co-circuit. And so if I have J is a set of T, a size T, if I take the union of these pairs that are indexed by J, I've got T pairs here, so the union needs to be a co-circuit. And so with loss of generality, we're just going to say that J is 1 through T. So the integers 1 through T. Okay, so SI has these two elements, xi and yi. So if I take x1 through xt, I've got t elements. And so by the t part of the S2ST2t property, I know that these t elements have to be contained in a co-circuit of size 2t. Okay, so I want to show that this co-circuit is equal to the union of these J pairs. But for contradiction, let's say it's not. Well, that means that there has to be some element yi that is not in the co-circuit. And so all the xi are there, but some yi that is not. And so I'm just going to say that that's y1 without loss of generality. So I'm going to let I be some subset of a complement of J. So anything from t plus 1 to n. So this is just a set of integers. And I'm going to let I have size s minus 1. Okay, so if I take the, so because of the S part of the S2ST2T property, because that S part, if I take S minus 1 of these, and then I take the union with this one extra pair, I have S pairs now. So this is a circuit, and it's going to meet C star. Okay, orthogonality is used a good bit in these couple of papers. So orthogonality, in case you're not familiar with, is the property that a circuit and a co-circuit of a matroid cannot have intersection of exactly one element. So these SI come from integers bigger than t. This S1 comes from 1 through t. And so we are going to know that the union of these SI has to meet C star, because otherwise then it would just be X1 in the intersection. So that would contradict orthogonality. So there has to be one of these other SIs that meets the co-circuit. So because of that, C star has to avoid at most S minus 2 of the SIs. And then because of that, based on the fact that our N is at least S plus 2T minus 1, the size of our co-circuit is at least N minus S minus 2, because there's at most S minus 2 that are pairs that are avoided. And this N is at least S plus 2T minus 1. So this is going to be greater than 2T, which is a contradiction because the co-circuit C star had 2T elements. So just a bit of a flavor of how a lot of these arguments go, a lot of use for orthogonality and so forth. Okay, so again, this is all showing how a little bit of a flavor of how we prove this. So if we have large enough matroids with the S2ST2T property, then those matroids have to be ST spikes. So let's look at some properties of these ST spikes. If M is an ST spike of order M, then that order is going to be at least S plus T minus 1. Okay, and for traditional spikes, S and T are both 2, so the order is at least 3, and so that's true for traditional spikes. The rank is going to be M plus S minus T. So again, with traditional spikes, and even for those T spikes where S and T are equal, then the S and T cancel out, and so the number of pairs is the rank. But in general, it's actually going to be M plus S minus T for these ST spikes. And since the total size of the ground set is 2 times M, that means that the co-rank is going to be M minus S plus T. All right, and if I have my partition into pairs, so this is the partition of the entire ground set into pairs, it's 1 to SM. And if C is a circuit of that matroid, well, then, of course, we know that any any S pairs form a circuit. So C is either the union of S of these side pairs, or there are other circuits that could come. These circuits meet all but at most T minus 2 of the SI. And again, for traditional spikes, T equals 2. So all but at most none of the SI. So with traditional spikes, the other circuits are transversals of the pairs. But here the other circuits do not necessarily have to meet all the pairs, but they're going to meet at most, all but at most T minus 2 of those pairs. And then with connectivity, if the size of our spike is sufficiently large, in K is the minimum of S and T, then M is going to be 2K minus 1 connected. Okay, a couple more slides with some more properties. The point of these 2 slides is that we know how to compute the rank of a set of pairs and the connectivity function of a set of pairs. So that's the point, but I'll just go through the results real quick. So here I'm using AI for the pairs, AI, SI. But here I'm just using AI. And if J is a subset of integers from 1 through M, then A sub J is going to be the union of those pairs indexed by the elements of that set of integers. So if I've got that, then the rank of this union of pairs, well, of course, if it's less than S, then it's properly contained in a 2S element circuit. So it's just going to be an independent set. So 2 times the size of J. We have J pairs, and so 2 times the size of J pairs. 2 times the size of J total elements. And you can work out that if the size of J is between S and M minus T plus 1, then the rank is going to be S plus the size of J minus 1. And then, of course, at some point, you span the entire matroid. And so the rank is going to be the rank of the matroid, which is M plus S minus T. We also know how to compute the connectivity function for these unions of pairs here. And if we have complements of a set in a matroid, then they have the same connectivity function. So we're going to assume that the size of J is less than or equal to the size of K, where JK is a partition of the integers 1 through M. And it so happens that if the size of J is at most T minus 1, then connectivity function is going to be equal to the rank function there. If we're between T minus 1 and M minus S, then there are a couple of subcases. If the size of J is less than S, then we're going to have T plus size of J minus 1. And if it's between these two, S and M minus T plus 1, we'll have S plus T minus 2. All right, and then if size of J is bigger than M minus S, then we end up getting M minus S plus T here. And again, the point here is just to show that we know how to compute those rank and connectivity functions. Okay, so one question that I haven't exactly addressed here is, do these ST spikes actually exist? The answer is yes. And we can construct them by starting with traditional 2-2 spikes and doing operations on them to increase the S and the T to get to the S and the T values that we want. So I've entitled the slide New ST Spikes for Mold. So I'm going to let M be an ST spike of order at least S plus T. And you can see here that where I'm going to go eventually is I'm going to have a ST plus 1 spike. So just increase the value of T by 1. Okay, so here is an ST spike with at least S plus T pairs. So order at least S plus T. And here's that 2-1 spike again. So got at least 3 pairs. And I'm going to extend the matroid by an element that blocks all of the 2T element co-circuits. One way you can do that, which is probably the easiest way, is just to freely extend. So here is E. I freely extend this matroid by E. And all of the co-circuits that I had are blocked. So without E, each of these pairs was a series pair, but now that's no longer the case. So E has blocked those all of those co-circuits. And then what we'll do is contract E. And now we are in rank 3, we're in the plane, and each of these pairs is, so every, the union of any 2 of those pairs is a circuit and a co-circuit. And what we actually get here is U36, which is a 2-2 spike. So I've increased the T value by 1 from a 2-1 spike to a 2-2 spike. And so this is kind of a silly or trivial 2-2 spike because we could change the pairs around, but it still qualifies as a 2-2 spike. So the result here is an ST plus 1 spike. Now the dual of an ST spike is going to be a TS spike. So if I do the dual operation, I'm going to have, if I start with the same ST spike before and I do the dual operation, I'll get an S plus 1 T spike. So what this means is that if I start with a traditional 2-2 spike that has at least S plus T pairs, say I want a 5-8 spike, then I can start with a 2-2 spike and I can repeatedly do this operation here to get my 2-8 spike. Just repeatedly do this. And then I can do the dual operation to take my 2-8 spike and transform that to a 5-8 spike. So ST spikes are going to exist for all values of ST. The spikes of all ranks do exist. Okay, so we said that the study of spikes and this SQTV property is motivated a lot by problems with connectivity. So here is a conjecture that appeared in this earlier paper with Nick, Rucker, Deborah, and Jeff, which says that there exists a function f of t such that if M is a 2t minus 1 connected matroid with no circuits or co-circuits of size at most 2t minus 1, and the ground state is at least this function, then either there's going to exist a t element set that I can contract or delete to stay t plus 1 connected. Okay, so I lose some connectivity. I go from 2t minus 1 to t plus 1. That's the conjecture, at least. Or M is a t spike. And so recall this results by Williams, which proves this conjecture in the case where t is equal to 2. So if t is equal to 2, then 2t minus 1 is 3, t plus 1 is 3. And circuits of size at most 3, so no triads, no triangles, etc. So I've got a chain theorem here in quotation marks and also a question mark. So this is perhaps a bit of wishful thinking, just based on the fact that this result was true in the traditional two-spike case. But seems perhaps plausible. But the less sure I am of conjectures, the more question marks I'm going to put. So I've got now 3 question marks. So seems to make sense that maybe we could generalize this to the ST situation. So we put this conjecture in here. There's just a function f of ST, where you take 2 times the minimum of ST minus 1. If your matroid has that connectivity, and there are no circuits of size at most 2s minus 1, or co-circuits of size 2t minus 1, and the ground set has at least that function size, then either, well, we're going to do contraction with the s's. So there's an s element set that I can contract and stay s plus 1 connected. Or there's a t element set that I can delete and stay t plus 1 connected. Or we have an ST spike. And so perhaps going down this path might be insightful in other areas, even if this conjecture is not true. But seems to make sense and seems to be a good generalization of that early result for traditional 2 spikes. And thank you very much.
Okay, so on the count of 3, let's all unmute and give Kevin a round of applause. 1, 2, 3. And are there any questions for Kevin?
I gave you a big matroid, and I just told you that all of the pairs of elements are both in a small circuit and a small co-circuit, but I don't say that it's the same. Is that likely to be highly structured as well?
I'm sorry, can you say that again?
So you've looked at various things. So like one of the things that forces structure is like if I tell you that every pair of elements is in a fixed size circuit and a fixed size co-circuit, then that's highly structured.
Okay.
What if I just tell you every element in a small co-circuit and a small circuit, and every pair of elements is in a small circuit and a small co-circuit? So I don't fix the size.
Okay.
That going to be highly structured, do you think?
I would be surprised if it was highly structured. I don't know exactly. I don't have a good feel for what that structure might be. But my guess is it would probably be. But yeah, that's pretty much just a guess.
Any other questions?
What are the minor relationships like for these spikes? So you have ordinary spikes and you contract an element and delete an element. Now you get a spike of one smaller rank. So I assume that you've got a similar sort of a thing?
That is something that we have not actually looked at very, very deeply, but there's got to be something similar to that, yeah, for sure. But off the top of my head, I cannot tell you exactly how it works. But yeah, there definitely has got to be some structure there where that works out. But yeah, maybe something else to work on to nail down.
Okay, thanks.
Kevin, can I ask a question about your first chain conjecture?
Okay.
So why is the T+1 connectivity in the conclusion the thing to shoot for here?
Well, yeah, so been a bit since I thought specifically about this, but the yeah, I'm sorry, I don't have a great answer for that.
That's fine.
Yeah,
Just
yeah.
one.
Yeah.
Any other questions?
It's probably, I mean, when you delete, every time you remove an element, the connectivity goes down by at most 1. So somehow, because there are pairs, I guess that's affecting the result. Instead of going down by t, it's going down by only t minus 2.
Yeah.
I mean, that's, but I haven't thought about this at all.
Yeah, that seems plausible there. Yeah. So right, yeah. So if you have this T element set, yeah, exactly like you said. So it could go down to possibly T minus 1, but we want to see if we can keep that connectivity, and so keep there to T plus 1 instead. So again, this is a kind of an optimistic conjecture, especially the other one. But yeah.
Any other questions? Well, I'll stop the recording and we can continue discussion off the air.